Welcome to qnawire.
In this problem on sources of magnetic fields, we are told that two long straight conducting wires are suspended from cords so that they are each horizontal and parallel to each other. They are also a distance d apart, and the back ends of the wire are now connected to each other by a low resistance connecting wire. A capacitor is now connected to the wire, and each plate is connected to one end of the wires. Now, when the connection is made, the wires are pushed aside by the repulsive force, and each of these wires now has a horizontal velocity, v0, which we are asked to calculate. We are also asked to calculate the height with which each wire will rise as a result of this connection in the circuit. So let's first recall that the current carrying wires will repel each other magnetically, which will cause them to accelerate horizontally. And since gravity is vertical, it plays no initial role. So for part A of this problem, let's first find the force per unit length. So the force per unit length, F over L, we know by definition is mu naught over 2 pi times I squared over the separation d. And so this can be written as mu naught over 2 pi times d times the root mean square current I naught over root 2 all squared. And so this becomes mu naught over 4 pi d, and I naught is simply v over r. So that's v over r all squared. We can write this potential difference in terms of the capacitance. So this becomes mu naught over 4 pi d times the charge in the capacitor q naught over c multiplied by the r that is already there, and that's all squared. So c is the capacitance on the capacitor. Now this is the force per unit length. So if we apply Newton's second law, we know that F over L is equal to m over L times a, where a is the acceleration. But the mass per unit length is lambda. So F over L is lambda times a. And this is mu naught over 4 pi d times q naught over r c. We're just repeating what we've stated above. So this means that if we rearrange this and we solve for the initial acceleration of the wires when the repulsive force becomes active, is mu naught times q naught squared divided by 4 pi times the mass per unit length lambda times r squared times c squared times d. Now that we have the acceleration, we can go to kinematics, and we know that kinematically the velocity v is equal to the initial velocity v naught x plus ax t. And this gives us the initial velocity v naught to simply be a times t. And we can write this as a r c. So if we substitute in for our acceleration in here, arc, we get the velocity v naught that we require to be mu naught times q naught squared divided by 4 pi times lambda over r times c times r times c times d. And here we have an expression for the initial velocities of each of the wires. So each wire will be pushed apart with a velocity equal in magnitude to mu naught q naught squared over 4 pi lambda rcd. Now we want to calculate the height to which these wires will be pushed. So we'll use the conservation of energy for part B. Now the conservation of energy simply tells us that the kinetic energy of the wires initially are half m v naught squared will equal to the potential energy at a later stage after they have moved off. So that's mgh. And rearranging this equation, we can solve for the height h. And this is v naught squared over 2g. We can see m cancels. But we have an expression for v naught squared. And so the height that the wires will obtain after being repelled apart is 1 over 2g into mu naught times q naught squared over 4 pi times lambda times r c d all squared. And that's our final answer.